Hello everyone, I am Omkar Deshmukh, studying in the first year engineering at MIT College Anandi, and today I am going to explain one of the most influential papers. Like all the AI tools that we use, ChatGPT, Gemini, Claude, or even the generative AI models, they are based upon this architecture, the transformer architecture, which whose research paper Attention is All You Need. It was published in about 2017, but it gains its actual importance when in the 2021 the OpenAI made the GPT, which was based upon this transformer architecture. So it's a very detailed paper. It has lots and lots of technical stuff as well as lots of deep ideation. So I'm not going to go in detail into any section. I'm just going to give a rough overview of its main points and what the paper was about and how it changed our idea of neural networks and made the potential wave for artificial intelligence and the future AGI possible. So I'm going to start reading the paper and highlighting the main points. So here I start. So, in the abstract itself, they say we propose a new simple network architecture, the transformer, which is based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. So, this is the revolution statement because before this model, we were having RNNs and CNNs or GRUs. So, everything was processed sequentially, right? Now we don't need recurrence or we don't need convolution, we just need attention. So in the introduction they have this line that says this inherently sequential nature precludes parallelization within training examples. So this was the real bottleneck. Like the older RNNs, they used to do the calculations and read everything one by one, but the transformer architecture allowed for parallel processing, and now that has made the way. So we are trailing to millions and now billions of parameters in the latest models of Gemini or GPT. So this is the real benefit of using transformer architecture. Now we can have a look at the architecture diagram. So on the left we can see the encoder stack, and on the right we can see the decoder stack, and they have described the encoder in a particular way. They are saying it as a stack of unequal to 6 identical layers, and then they have said we employ a residual connection around each of the two sublayers followed by layer normalization. So each layer is having a multi-head self-attention as well as it is having a position-wise feed-forward network. So this design is actually combining the attention as well as the residual connections and the layer norm. So this structure of repeated blocks is exactly how the GPT model is working today. So now we can have a look at its overall mathematics, where they have said that the attention with q, k, and v is the softmax function of q k to the power t and under root dk of v. So basically, q is the query, k is the key, and v is the value. These all are the matrices. So there are two things happening here. So uh, there is a dot product which is measuring the similarity, and then there is soft max which is turning that similarity into weights, and when we take that weighted sum as values and we repeat it, this makes the engine behind GPT. Now uh, we move on to the section 4, where they are comparing the architecture. They have shown that the self attention requires a big O of one sequential operations, while the recurrent layers required big O of n sequential operations. So this is the actual breakthrough of this paper, where we are having shorter path lengths. Everything is more, you can more make it parallelizable, as well as there is this better long range dependency learning. So that's why the transformer can be scaled like exponentially faster than the traditional RNNs or CNNs. Now, at uh, the results would be that when this was, they have reported our models achieve 28.4 BLU on the WMT 2014 English to German translation work. So they gave just a translation example. At that time it bet its prior models in the translation, but no one in the 2017 was talking about general language models. They just saw its way for the translation and stuff, but now it has grown to this vast large language models, where we have moved a lot beyond the simple translation. Everything like from coding and reasoning and natural human like interaction is possible, that too with fast speed right now. So that's the very brief overview of this transformer architecture paper. And at the end, um, I would like that uh, everything that we call a large language model today traces back to this paper. So studying this paper needs needs background of knowing machine learning and little bit of mathematics and some technical stuff. But once you understand that yes, nowadays it is implemented and new models are coming, but once you understand the idea that how they were able to get from the simple NNNs to this paper, you can borrow the same first principles and make ideas and betterments for the future of AI model training and so on. Thank you.